Hello, everybody. How's it going?
Going good.
Hello, hello.
All right. So, are we all here? Let's see. We got a chat going on off to the right so that we can collect comments as needed. There it is down there below. Okay. All right. Good deal. Well, let me try to fill in kind of where we're at right now by sharing my screen, and then can you guys see the data page there? All right. So just a quick rundown to make sure everybody's on the same page. Well, actually, maybe I should turn the time over to Michael really quick. Michael did the most recent kind of uh, adjustments to our method for collecting data and stuff. Michael, are you there?
Yeah, I'm here.
Did you want to talk us through something, or should I give a little introduction first, or
I
what did
can
you want
do
to?
I can do a small kind of
Okay, great, excellent.
thing. So basically, I checked most of the data that has already been done and our temperatures. As you can see, they're very different. We don't have those X marks anymore and whatnot. So I just got rid of all those. Um, and I set up a little key to the left on the calc page, and that just gives a color code. We can use it. We don't need to. Um, but that basically kind of self-explanatory. So if you go down to the temperatures, like say you do Hemo 29 and you finish the testing, you would mark this space to the right of it. You would put it as like a purple, and that we now know is done and ready for the first analysis. And then you would analyze it, the first analysis, and mark it as green, and then so on. If there's a problem with the data, it's yellow. And then same thing with the bottom. So on your tab, you would mark your tab the same color. So, so we know also that it's ready to be moved on to the next stage. And then there's points to check again for analysis one. So I figured those out just from the graphs at the top. Some of the points didn't make very much sense. So these are just points to kind of look over at analysis one again, make sure we got the slope correctly. And if not, then we gotta maybe redo those points. Um, that's essentially it. And then I have the ask about Mayo 30.45 because I don't know what to do with that one. That one's just a little weird.
Yeah, in terms of, let's see.
The temperature and let's see, I think the data just looked really wonky. I could be wrong, but maybe it was just the temperature that I was like, I don't know what we want to put it as because the 0.45.
Uh-huh. Okay, so I'm just looking at the data here. Quite interesting there. All right. Hmm. Okay. Get back to the
Does that make
um
sense with the color coding though?
it makes sense to me.
Yeah.
So for these points here, currently, myoglobin at these temperatures in Celsius, and sorry, hemoglobin in these temperatures in Celsius, and myoglobin in these temperatures in Celsius, we have the analysis have been done completely, and we plotted the points over here in these graphs, right? Now, according to nature, right, unless there's something that we're not seeing, which is very unlikely, these plots, we don't have them labeled here, but this is the See if I can do that really quickly here. That's something that's going to take more time than I want to spend right now. Yeah, I can't do that very quickly here in this wonderful Microsoft 360. I can't see where to do that. But on the x-axis, we have temperature in Kelvin. And on the y-axis, we have the natural log of the Vmax. And these plots should be, let me bring up kind of what we've seen before with these. So these are some of the plots that we've seen before. These plots should probably be, either linear, like here's our myoglobin pH 7 that we collected data before. And this one here, I thought perhaps was not appropriate. I thought maybe the linearity of this was incorrect and that there should be some curvature here. But it might be that that's the case. So if we take this one, for example, here and look at or put it in this space here, see where we're at. So we have a span right now from starts maybe, if I were to put a linear fit to this right here, be about 3, comes up to 6, from about 290 to 320. So how does that compare to this one here? 3 to maybe 6. Now see, we weren't getting that high for myoglobin pH 7 before. It was just in this space. So this data, which does seem a little bit thicker than this data that we had before, but they both seem to be linear. So it might be that this is linear, but it's really hard to tell. So, but the data should either be linear like this, or we should see a point where we get a maximum and the points start to come down. Now, we're not going to be able to enrich this right side of the curve because at high temperatures, the hydrogen peroxide begins to decompose by itself, and also the myoglobin or the catalysts begin to degrade at these higher temperatures. So we're not going to be able to fill it in, but if we can convince ourselves that we actually see a maxima and we see the points start to come back down, that's all that's necessary. We know the symmetry of the curve. We know the general equation that this curve should fit this thing right here. Okay, so that being said, minimize this. It'll be here. We'll leave it here for references if we want to talk or think about it later on. But that being said, these are hardly looking like either of those. And so let's look at our temperatures again. We were getting upward towards 330, 340 degrees Kelvin. Looks like that's about our maximum there. So we would like to push a little bit higher to get up to about 340 to see if we can see that curvature. But yeah, the data is a little bit concerning. Not because we're not seeing curvature. If we don't see curvature, that's fine. But we just shouldn't see this sort of a spread. For example, a pH, the hemoglobin here on the left. I just don't. I mean, this doesn't mean anything, right? This should be a portion of a linear curve here, or again, a portion of a curve that's going to begin to peak and come back down at some point. Yeah, I mean, there shouldn't really be any other scenario associated with that. So I don't know. Do you guys want to give your best guesses as to what might be the issue associated with the data that we're collecting right now, or the results that we're getting? Anybody want to comment? Yeah, go ahead.
Well, for me personally, I think especially when we start working at more extreme temperatures. I feel like it gets kind of tricky to get the temperature that we want. I feel like temperatures kind of start to fluctuate a little bit between each cuvette. At least for me, that's been like the experience. And I've tried to like I've gotten better at it, but I still feel like that could be one issue that affects the data a little bit. At least with myoglobin. I haven't really worked on hemoglobin too much, but for myoglobin, that's been my issue personally.
Okay. And Michael, let's see. I'm trying to scroll through this to see if anybody else has their hand raised or anything. I can't seem to. Oh, there's the button down there. I mean, anybody can just speak up if you want to. You don't need to be called
Yeah.
upon.
I have a. Can you hear me?
Yes.
With the hemo, it may be because we were starting on hemoglobin at lower temperatures, so then our like accuracy and efficiency wasn't as good as myoglobin.
Okay. So because we collected this data earlier on, then and we were kind of just cutting our teeth, learning how to do it. We might not have, this data might be a little bit all over the place, whereas this is an improvement upon where we might have been. Is that the idea, Ben?
Yeah, that's what I'm thinking.
Yeah, I would agree with that. Any other thoughts?
I mean, also just looking at this, we have almost double the point density for myoglobin. Whereas with with hemoglobin pH 5, we have like about half and only like 6 unique points there.
Yeah,
So if we could just get a much higher point density for hemoglobin, we might see our predicted curves start to show up.
yeah. Because
And
I
then,
mean,
yeah.
yeah, I think that's probably right. Because for sure, I mean, I can't imagine how this lower point is correct. For example, right? Good observation. Any other thoughts or observations? Okay, so some of my concerns, which I'm not sure about, but I know that the other day when I think it was Ben was working, he noticed, and I can't remember what brought it to his attention, that one of the pipettes was off by about 20% in terms of the volume. I think it was the P1000, the 1000 microliter pipette. And we went and we got a new one from the stock room and traded out that old one. But that was something that we were trying to demonstrate how we could check the accuracy of the pipettes on our first couple of days that we met. We would just identify a volume and deliver that volume onto the scale and find out its mass and see how that related to the volume. So just a side note, that balance that was next to the sink got taken away kind of as a mistake. And they said that it was going to be returned. Has anybody noticed if it's been returned lately? Has anybody been in there lately and noticed whether it's been returned or not? So okay, I mean, I'll follow up on that again to verify that that's going to actually come back. I think a group took that thinking that was their balance or something, or maybe a temporarily thing, but yeah, that balance needs to, I think that it's appropriate for that balance to stay in that room, and we need that balance, or we need a balance. We do have access to the balance in, let's see, the biochem lab. What is that lab where we're storing our catalysts? Anybody remember that number?
160, 168.
168. So there is a balance in there. And we can use that one. It's a long walk across the hall sort of thing. But we need to verify that our volumes that we're delivering are right on, right? I mean, less than, or 10% error max, I think is where we're at. So if actually, no, less than, or it should be about 5% error. So if I'm delivering 1,000 microliters, I shouldn't be off by, I should be off by, maximum 50 microliters, right? So, yeah. So again, 1,000 microliters should have a mass of 1 gram, right? That's 1 milliliter, 1 gram. So I'm delivering water, right? And that's what I'll use to test it. If the mass is between 1.05 grams and 0.950 grams, then that would be our 50%. I think, or sorry, 5% range. So I think I said that right. But make sure that, and I think we should be better than that. So that should be our outer limits of where we would be comfortable. And the same 5% range for our P1 or P200s, P100s, P20s, right? So we have to make sure that those volumes that we're delivering are within that 5% range or less. The other thing I'm a little bit concerned about is our hydrogen peroxide concentration. I'm not terribly concerned about it. I feel like, you know, the V maxes themselves. So if we choose a data set here, maybe we go into myoglobin 31, all right? pH 7. If we choose a data set here, I think that most of us know how this data is analyzed, right? But we look at the data that's been collected and we try to get a fit that we think represents this slope here. So this slope here, if we were to take 0 to 10 seconds, it would not be a good representation, for example, right? Because the line would probably head off in this direction. If we were to take 0 to 40, it might be okay. But I think in this, probably this case, this range in here, 60 to 80, would probably be the best bet. If I took 0 to 100, that would probably give me a similar line as 60 to 80. And so that would work as well. But then after we identify the range that we want to take, for example, if I were to come here and grab the 60 to 80 there, copy that. This is Myo 31. I'll take and bring that over to the calc sheet, right? Myo 31 pH 7. So here in the calc sheet, I would find Myo 31 pH 7. And not everybody has been introduced on how to do this, and that's okay. We don't need everybody doing this. It doesn't take nearly as much time as data collection. So we need more hands on the data collection. But let me, just for an example, let me try to find the Myo 31 pH 7. Michael, you also had the opportunity to go through these and see what percentage of these were analyzed, right?
Yeah, I don't think I got like percentage, but we looked through all of them and figured out what ones needed to be done or not. I
And
coded them on the bottom also, like the colors, I guess.
the colors are coded. So it looks like pretty much all of them are been addressed somehow, right?
All of them have had the first test. And then the green ones still need to be run through like the kaleidoscope
Okay,
or kaleidograph. There.
yeah. So I'm still searching for the Myo 31.7, or what is it, 31? Which is Myo 31, right? Okay, here we go. So, see if I can shrink this down to size a little bit. So here's Myo 31 pH 7 corresponds to this sheet then down here. Taking that data, and we don't need everybody doing this again, so don't do this, but that data will be pasted in this space right here. So this is 28 to 47. And I didn't look particularly at that. We can look at the 28 to 47 and see. I don't know, that might give it to us. I'm not sure. But pasting that in the space here that this equation will collect from the data that we paste the slope. And once we paste that there, the data again gets pasted right here, this space. This will collect the slope and it will be propagated up here. This slope, which is in the rate of absorbance is 730 nanometers per second. All right. Is converted to molarity of hydrogen peroxide per second. And then that's plotted against the concentration of the hydrogen peroxide. All right, this is done for all 6 of our concentrations of hydrogen peroxide. We get a 0, 0 point because we blank our cuvette. And then this plot here should be able to be fit with the Michaelis-Menten curve following saturation kinetics. So when we fit that plot, so if the data here, right, if the data in the myoglobin 31, for example, again, is not really maybe representing these slopes well, if it's been collected in a slightly wrong spot and the slopes don't represent well, then like that's a nice easy one. That's a good one there. One note on something like this, there's not very much of a decline towards the end, but there's a slight decline. It's a little bit of a curve. And so whenever you would see a situation where there's a little bit of a curve, you'd want to take the data more towards the beginning. It begins to taper off as time passes because the concentration of hydrogen peroxide is changing as the reaction occurs. So just a small thing, but anyway, this is our semblance of a saturation curve. And then this data here, which is green because it hasn't had the fit to it, right, Michael? And we turn it blue when it does have the fit. So it looks like there's some green here. For those of you who know how to, let's see, who do we have here? Maddie, are you here?
Yep, I am.
Okay. Are you doing, I guess you said you weren't doing any of the Michaelis-Menten fitting, just doing the green, the initial step right now, right?
Yeah, I mean, I might have a little bit more time now, but the last few weeks were just absolutely insane. So if
Okay.
you want me to do the second step, I can look into that again.
Well, if there's any of these whose green step we're kind of concerned about or doubting or have lower confidence in, you
Yeah.
want to definitely get in there and just verify that those points represent the data well, first
Okay.
of all. That's what we need to do first. Michael, do you feel like we did that really well already? Or that'd be a waste of time if she went and did that again? Or
So there's points at the front of the calc page that I listed to check analysis 1 again. Those points I looked at and I don't know, they looked really weird on the graph that we plotted, and so those points are good to look at, but other than that, yeah, those ones right there. Yeah.
Okay, so
so
I'll go through those couple right there.
all right. Okay. So after we get the data, so here's another set here, Myo 21, pH 5, the first one. This is what the resulting data look like from those linear fits. Then we fit it into a program that will give us the Michaelis-Menten curve here. Trying to look, I have 2 of these. Yeah, that's just fake. So Mile 3 or Excel 365 brings up ghosts every once in a while, and if you think it's not a real figure that's supposed to be there, it'll disappear if you just click on it and then click off of it. So, so those other 2 that were there were just brings them up every once in a while. All right, but this is our fit that we get. All right, when we fit the Michaelis-Menten curve. Now, if we look closely here, or if we get in a little bit closer, we can see some of these values. M1 is the Vmax And again, what we're looking for is where this line would be predicted to saturate based on Michaelis-Menten kinetics. So 7.8, it looks like it's kind of saturating. Specifically, it says 8.7 times 10 to the minus 8. That's our M1 value here. And then based on the data, it gives us an R squared value of 0.96. Now, I'm not sure that we can use that R squared value to any confidence, but it might be the best tool right now that we have, where we can say, okay, if the data is below 0.91 or something like that, below 0.9, then we say we're not going to be using that data, for example. I'm not sure if that's a take-home standard at this point, but we may pay close attention to that and kind of make a decision about whether we need to, if that R squared value becomes something that begins to kind of stand out. For example, if we start looking at some of these points and seeing that the data is not working. So the short of it is we need to thicken up this data and figure out what's going on. We won't get rid of any points at this right now, but I do think that we need to, with our focus on improved or just verification that the micropipettes are giving the right volume. I think that's the one thing that we really need to focus on. And then the other thing along those same lines is we really need to be careful about when we do the delivery and the movement of our solutions, that we watch the volumes. Watch the volumes. Go slow enough so that we can watch the volumes come into the pipette and then go out of the pipette. I think we're okay with mixing. Mixing is oftentimes an issue with why the data doesn't look good, but I think we're okay there. I don't think that there's any reason. So let me talk to you about why mixing becomes such an issue. If, for example, the substrate, which is hydrogen peroxide, is placed into the container in close proximity to the, let's say, the enzyme, let's say, if they were squirted into the exact same portion, then there's a possibility of kind of just a minimal amount of side reaction, but you could decrease your concentration of hydrogen peroxide perhaps. And so theoretically, if you didn't have a good mix when that occurred, you might be changing the concentration of hydrogen peroxide and get a slightly different rate. I think these concerns are significantly minimal for our assay, for our specific assay. So I'm not super concerned about it. That's why we've been just focusing on mixing the way we have been. I think it's okay. Heating for a long period of time, I do think that could be an issue. So we don't want to heat our samples for very long at all. We want to get the bath heated to where we think we need it to be. And usually that means, or heated or cooled, it means above or below the temperature that we're after. And I think, like Jacob was saying, getting that temperature to be right, probably choosing a single or working with one cuvette at a time, where we raise it to the temperature that we want, and then we take it out right when it's at the temperature we want. We deliver, and the time that it takes to reach that temperature should be less than 5 minutes. If we can't get there, then we have to adjust the temperatures so that the cuvette can get to the temperature it needs to in less than 5 minutes, and then we can get it out and mixed. Is that a new hand up, or was that the same hand up? Jacob?
That's mine. That's mine.
Is that new or
Yeah,
the same one?
It's new. It's new. Yeah.
Okay, go for it.
So yeah, I think with that, when it comes to heating, especially at extreme temperatures, it's probably best to use the heating plate. Just because the water bath, it's a lot trickier to use at higher temperatures. And also I forgot what it's called, the thing that like stirs the water around it. Like we're not supposed to overheat that because then it will turn off.
The pump, yeah.
Yeah.
Yeah, so higher temperatures. I think that's right. Use that water bath. Sorry, the stir plate, the large beaker, right? Good. But yeah, we can't keep all of our solutions in the temperature bath for more than 5 minutes. So we got to find out what it takes to get the temperature quickly up to where we want it or quickly down to where we want it. And then remove it fast out of the compound or the volume that we're going to add, and then mix fast and get it into the spectrometer fast. Okay. Yes. Who is that? Colin, go ahead.
Yeah, I think the procedure that me and Grant worked on or worked with, it was one that worked particularly well for high temperatures because you would do each cuvette one at a time in like, if you wanted to do like say 45, you would just get like a single 50 ml beaker and then stick that on a hot plate and then fill it with distilled water and then heat it until it's like 80 or something. And then you would just take a single cuvette with a thermometer inside it and then put it in there until you hit like a 50-degree internal cuvette temperature. Then you'd put that in the spectrophotometer and wait until it dropped down to 40. And then you would add everything and react it.
That sounds good.
Yeah, you end up with the cuvette in the heating bath for a lot less time. And it's also, if you're doing like 6 back to back to back, it's I think it ends up saving a bit of time because you don't have to fiddle with like taking every cuvette individually out of a mechanism or getting them all to heat at the same rate in the same area.
Okay, good. So having a source of temperature high, 80 degrees, for example, putting the cuvette in there and watching with the internal or a thermometer right in there, watching it when it reaches the temperature. So if I want, for example, to run a reaction at 45 degrees, tell us a little bit, Colin, about how high the temperature needs to be if I'm going to be adding the ABTS at room temperature. So, or as opposed to, we talked about this before, Colin, you and Grant, about the ABTS coming in cold or coming in at room temperature. Do you want to comment about that?
I think because I remember once we tried to standardize it, but the problem is that depending on the temperature your ABS starts at and the temperature you're heating up to, the magnitude of the temperature drop is going to change. So what we ended up doing is that we would just try to keep the ABTS we were using at around room temperature, and then we would always go by the temperature that the assay was at the start of the reaction.
Okay.
And we would just put that down as the temperature we were using, because even if there was temperature drop, it would be uniform across all the points.
Okay.
Because what we were adding was the same temperature. Also, regarding what I said about the heating procedure, don't use distilled water for that. That's a bad idea because it'll bump if you heat it up too high. Then just use tap water for that.
Okay. Good. All right. So just to recap on that, then, high temperatures, maybe 80, maybe not up to 100, not near in the 90s, trying to keep it so it doesn't boil on you or whatever. Tap water, a little bit of salt in there to decrease bumping. Bumping is where you get kind of quick boiling. So superheated conditions that when they get disturbed, it'll splatter and can spit out on people and burn them. That's our source of heat, one cuvette at a time. Thermometer goes in until we reach the temperature that we want to have. We add the ABTS, make sure the ABTS is thawed and at room temperature. So don't keep it on ice. All the ABTS that's not being used, yes, we'll want to keep on ice. But the ABTS that we're going to be running assays with, try to get it to, we don't want to heat it up because that will begin to decompose it. But if we just get it at room temperature, then its impact on the assay or the rest of the components, the temperature will be minimized. And then we report the temperature right before or right as the assay begins. We don't need to worry about finding out what the temperature is after. We know it's not perfectly uniform, but based on the data that they were getting before, it should be, it should work out fine. You know, there is a thickness to our data, right? We see that there's an amount of data. I mean, you know, in terms of amount of error in this data, but that's all right. We know a lot about the shape. We know that it should be pretty symmetrical on both sides. So we just need to kind of guide that line with enough data. And yeah. All right, Jacob, did you have some more to say?
Yeah, so just to clarify, so if we are doing more extreme temperatures, like we would record the initial temperature rather than the waiting till the end. Did I
That's
hear
right.
that correctly? Okay, cool. That helps a lot. And then is there an
Now,
issue of,
you
whether
can't, okay,
oh, go
so
for it, sorry.
before you get on to off of that, you
Yeah.
can't, I mean, if you wait and try to let the thermometer adjust to the temperature after you've added the ABTS, you might miss the true rate for that reaction. So Colin, how would you guys do that? Would you just take a sample of just distilled water, or one sample, sacrificial sample, that you would run to check how the temperature would be affected by everything? What would you do there, Colin?
We're talking about getting like the true temperature drop for a point, right?
Right. Well,
Uh,
not the true temperature, but I mean, like you said, the temperature that you had right as the assay was beginning was the temperature you reported. But how would you get that after you added the ABTS? Or would you just assume that the ABTS was part of that understood temperature drop?
oh, the point at which we recorded the temperature was before adding the ABTS while it was sitting in the spectrophotometer. That's
Okay.
when we recorded the temperature, and that's what we put it down as. So no
Alright.
ABTS was added at that point.
Okay, so yeah, if we just keep the ABTS at room temperature or maybe even slightly warmer, then yeah, that I think that's fine. I mean, I think that we want to get right at this point is just a consistent method that will begin to give the semblance of the curves that we're looking for. Okay, Jacob, sorry for interrupting you there. Anything more?
No, it's all good. Are there any concerns with like letting the cuvettes heat up with the caps on? Or is that like okay? Like does that affect the temperature at all or anything like that? Or
I haven't
I don't
seen
think
that that's
so.
an issue. I don't think that the
Okay.
volume change is going to be significant
That's
enough
not gonna do
to,
anything.
I
Okay,
think we're
cool.
okay.
Okay.
Colin, if you've seen anything different, you can chime in there, but
We've never tried heating with caps on, so I don't know if there would be problems with that. I mean, I'd assume any volume change is negligible, and even if there was, the cuvettes would be strong enough to contain it.
definitely strong enough. And I don't know that they're really how strong the seal is. So I think that I don't think there'd be gas seals, is what I'm saying. I think that as the pressure built up, that it would slowly leak out and we wouldn't even have any detectable amount of you know, gas pressure buildup. So okay, great. Any questions or comments about what we've been talking about? If you're lost and you don't know what's going on, we need to make sure we hear from you because
Can you all hear me okay? Just want to make
yes,
sure
go
that
ahead.
first. All right. So, you all probably saw me during like the first 2 weeks. I have a bad immune system. I was hit with a respiratory infection very soon after. So, I've been out for like close to a month now, but I'm off my antibiotics as of a few days and I'm ready to get back into it. But I'm going to be honest, it's been a while. So, if people are coming in like the next 2 or 3 days, like let me know or email me because I would love to come in, help watch get back on track because I'm not confident doing it alone at this moment. So yeah, is anyone coming in the next few days and would be willing for me to tag along?
I'm always there from 2 to 4, usually Wednesday through Friday. So if you're gonna be
Okay.
there around that time, you can. I
All
know,
right.
I think Jeremy might be joining me too. I'm not sure, but
Gotcha. That's perfect. You'll probably see me one or two of those days. And yeah, that's all I wanted to say. Just glad someone's there and I can catch back up with everything.
Yeah, along those lines, I've been we want to have an increased chance of people being able to work together. So I mean, the initial approach was to try to help everybody feel confident of saying, I'm going in at this time, I'm going in an hour, I'm going in whenever, so that others would feel, confident that, oh, I'm not sure about this, but now I can go in and learn a little bit. I feel like that hasn't been happening, that people aren't emailing when they're going in every single day, and maybe because they feel like it's, it feels silly or whatever, which maybe it is silly. I don't know. But would there be a better way for us to communicate with each other when we're going in? If we had a calendar, I mean, I don't want to have any of you feel like you have to show up all the time, or even have to show up when you said you were going to, but something came up. It's summertime. I mean, if you're doing something, you're doing something, right? That's, this isn't above everything. But yeah, I do want to have the opportunity for everybody to find somebody to work with, A, and B, I want to be aware of when the best time for me to come in and kind of just check up on things is as well. Anybody have any suggestions about the best way to kind of make it known that we're coming in?
I think a calendar actually sounds great, personally.
I agree with that personally. It even just knowing, oh, hey, I'm coming in usually on these days, 2 to 4. That really helps me to get back in the swing of things and work with people. So maybe an updated availability sheet now that we've gotten actually into the swing of things. We all go back to where we initially noted our availability, or even just a comment saying, I'm usually here these days, these times.
Okay, any other comments about that? So I will we'll repurpose this tab here, this availability tab. Is that okay? Do you think we need all the days on here? I mean, if we have all these days like this, just have everybody's name. Let's see. Is this okay? I mean, I don't know. I feel like, well, why don't we put in the days that we're kind of just generally thinking about coming, or maybe this is already it. I'm not sure. I know that there's a couple people. Let's see. Who do we got? Yeah, Colin's not here. Constanza's not here. Yeah.
I think availability is a lot different than days you're planning on coming in. Like these are all times that we can come in, but that doesn't mean we're going to. So I
Okay.
think we all need to update. This is the time that I'm planning on coming in. Maybe not as a weekly thing, but maybe, I don't know, just make our times more specific in that regard.
Okay. So we'll call it planned research times. Is that okay? Is that looking okay? Okay. Does that look all right? Any comments or any concerns about that? Okay. So, let's see. I want to give some time now to talking about the paper and where it's at right now. All right. So let me see if I have, here it is right here. So really quickly, give me a thumbs up. Do they have that as an option? I don't know. You guys all have, I mean, you just speak up because I can't really see what's your thumbs up necessarily. If you don't, or if you haven't looked at the paper yet, be a big kid and fess up. Not because I'm mad at you, but because I just want to know where we're at, right? So has anybody not looked through this?
I have not looked through this.
Okay. Anybody else?
Me neither.
I
Okay.
haven't, no.
Okay. 3. Anybody else?
I also have not looked at it yet.
Okay. All right. So that's
I
you know,
heard briefly, but not too much.
sure, about half of us. So we're going to begin to become familiar with this paper. All right. Colin has his hand up. Probably something important. Go ahead. Is that Colin? Oh, Cal. Sorry. Go ahead. Did you want to say anything else, Cal? Or you were on mute. I'm not
Oh,
sure. I saw
sorry.
Okay.
I don't understand. I thought that was.
Oh, the thumbs up. Yeah.
Yep, I figured
Perfect.
it out.
Yeah. Okay. All right. So, yeah, I've asked Colin to try to finish up the introduction here. Colin, do you feel like that's where we're at right now?
I think it's at a good stopping point. Whether or not it needs revisions is going to be subject to your discretion. But
Okay, great.
Yeah.
Excellent. And you know, we've gone back and forth a little bit. So I would probably bet that we're at a good place here with this introduction. Okay. I think everybody reading the introduction will help us have a little bit of a better understanding of what we're trying to accomplish. Okay. In terms of data, the only data that we really need for this, Colin, is lipo-pH. No, let's see. What are the datas that we need here? We need these three, the pH 5s, which we have already for everything, but we don't have hemoglobin. And then we need the pH 7s, which we have old pH myoglobin pH 7. We have lipo pH 7. We don't have hemo. What was it? We can't see this one. So we do have some hemo pH 7. But we had a little bit more than this, didn't we, Paul? This is the older data, right?
we may have gotten a few more points. I can't recall though. If
Not-
this is from the 2023 presentation, then I think so.
Yeah. So we have a few more points here. We'll have to take a look at that. But I mean, if we don't get by the end of this month, I want to have this paper ready to submit somewhere. All right. So we got about 15 more days. I want to be able to submit this somewhere, whether that be with the data that we already have, which would be just lipo pH 7, myo pH 7, lipo pH 5, which I think is this right here. Oh, the copper ion pH 5. This is lipo pH 5, and then the myoglobin pH 5. So we have enough data, I feel, to submit regardless, and I want to keep on track. So this paper will be ready to pivot towards that. Really, the only data points that we needed to kind of top this one off that we were hoping to have were the hemoglobin pH 5, and that's it, the hemoglobin pH 5. The myoglobin pH 7 was trying to really ensure that this data was correct, because it just seems like it doesn't fit. It seems like it shouldn't be linear. But if that's what we see, we're not going to keep forcing it into something that it's not. So does that make sense, Colin, in terms of being ready to pivot if we need to, if we don't get the heme pH 5 data to work? Is that okay?
Yeah, that makes sense to me.
Okay. All right. And then, let's see, the introduction is all right here, right? And then I have asked, so now we're going to be turning, if you haven't mentioned or done anything, Colin, in the materials and methods or the results section.
I haven't worked on that yet.
Okay. So I'll look over the introduction. Everybody who hasn't looked over the introduction, look over it as well. If there's any questions or concerns, email them to me and we'll get through them. If I find anything, Colin, then I'll forward it on to you. But yeah, if we want to turn our attention towards the materials and methods section, and or maybe just the results directly, depending on, I feel like there's a lot here that we can, in the materials and methods section, there's probably enough that we can deal with and be, enough to get us, it's got a much stronger start than the results section has, at least. And then I talked to Sims. Is Sims here today? Where's the list?
Yes, I'm here.
Awesome. So, right, you were helping with the references, right? Is that you?
Yes, yeah.
Awesome. So, did you get to do this first reference here?
Yeah, I did that first one.
All right. So everybody is welcome, and I would be encouraged to follow this pattern of reference and creating all of these other references in that pattern. Did you get to do any other Sims so that people wouldn't have to waste time on them, or?
No, I haven't done any others.
Okay. Yeah. Trying to get all the references is a place where time can be spent. This is just bibliography stuff. We're not going to have an official training on this. I just try to follow this pattern, the first pattern right there. I'm going to stop sharing my screen really quick to see if there's any questions about how you might contribute to the references there, for example. Any questions about that? I feel like that's something that everybody could do. I mean, we're not talking about finding new references. It's just a formatting thing right there, right? Okay. All right. Is there anything else we need to talk about, Colin, in terms of the paper?
I think we've addressed most of what we need.
Okay. All right. Well, where are we going to spend our time? I think what I want to do at this point, especially with what I've seen with the data thus far, I think the myoglobin pH7, if this is real, if these points are wrong, if this is real, but we're just having some trouble with something, it still seems like it's pretty linear, which is similar to the data we had previously showing that it was pretty linear. So the best piece that would fit for us right now would be the hemoglobin pH 5. That's the MES buffer, right? Hemoglobin pH 5. So I'd like everybody to focus on collecting data for the hemoglobin pH 5. That would be the best component to fit right in with the rest of the data that we already have, because we have all the other three catalysts, lactoperoxidase, myoglobin, and what's the other one? Copper ion at pH 5. So if we had the hemoglobin at pH 5, that would be good. And then this might not be as strong as we would like it, but I think we do have 2 or 3 more points on there. So that'll be good enough. So everybody, if we're going to go in and collect data, let's collect it for hemoglobin pH 5. We only have this many completely done, but right now I'm not sure that I have confidence in. I don't know what to have confidence in. I feel like there must be at least a half or a third of these points that are legitimate, but I just don't know which ones are incorrect or which ones are suffering. So in terms of new data collection, I think that's where we want to be. All right. Excellent. Anything else anybody wants to say? Okay, thank you guys so much. We're all going to go and fill in not our availability, but when we generally show up or are planning on generally showing up, so that others can kind of feel more comfortable showing up together. Any other questions or comments? Okay, great. I'll see you around. Yeah, fill up that sheet so that I know when the best time is to come in and see how things are going. Okay, be
Thank
sure
you.
to
Thank you.
recalibrate your
Thank you.
micropipettes. Yep. See ya.
Kevin,
Bye-bye.
thank you.
Thank you.
Yeah.
Mhm.